Hi guys, and welcome to Mindset Learn Extra. This is grade 11 maths. Tonight's show is brought to you by Liberty, and last week we covered simultaneous equations with Heather. Tonight our topic is transformations, and Yuval will be taking us through it. Hi Yuval.
Hi Indiana, it's good to be back. Of course we're doing the exciting world of transformations. That is things like enlargements, things like rotations. It's grade 11, so for those of you in grade 11, this is potentially new work. It's part of the syllabus for the year for grade 12s. It's examinable just like all the rest of the grade 11 work, so you need to pay attention to this hour too. Of course, you've got your own hour coming up afterwards, but this is going to be just as good.
Exactly what I always say, learn more, learn extra, right? Guys, please only call and send questions relating to this topic. If you stick with us throughout the year, we'll eventually get around to the section you're having difficulty with. Next week, our topic will be analytical geometry, and lots of you have been asking about our schedule. So if you are in a study group, the topic next week is analytical geometry. The show tonight will start off with a lesson on transformations, and then after the break, we will work through an example or two. Lastly, we'll be tackling your questions in the last 15 minutes, guys, so please make sure that you get them in and please make sure that they are relevant. There are lots of ways to get hold of us. You can get hold of us on our Facebook page, that's facebook.com/learnextra. We're also on Twitter @learnextra. We also have a fantastic website. It's www.mindset.co.za/learnextra for all your needs. If there's anything you want to download, go to that website. So, shoot those questions off to us and we'll get round to them in the third part of the show. I also have an amazing Casio calculator to give away tonight. It's one of the best questions posted on Facebook. We will be announcing the winner tomorrow on the page. So after the break, we'll be back with Yuval. Hi guys, and welcome back to Learn Extra Live. Today, right now, is grade 11 maths, but grade 12s you should be tuning in too. I just want to give an extra big shout out to Liberty Live. Thank you so much for making this all possible. It's amazing, and we're going to have an awesome session today. Guys, don't forget to get all of your questions in on the page @Learn Extra. Please make sure they are relevant to the questions that Yuval is going over. It will make things go a lot quicker. Okay guys, let's get straight to Yuval. Let's get this lesson started.
Okay guys, so we said before that we're doing a lesson on transformations. The first transformation is a rotation, and I've got some basic facts here that I think we need to know just to start off with. So 90-degree rotation clockwise, the image of a point P, X, Y rotated clockwise through 90 around the origin is Py, negative X. We write the rotation as X and Y minus X. So it's quite easily explained by picture. So if you have a point P, X, Y, okay, and if maybe we can put a coordinate on here. So looking at this diagram, I mean it's approximately -1 in the x value. Okay, so -1. What is the y value? Well, 1, 2, 3. So that gives us a coordinate of. Let's just see if we can get that back in. Okay, so we said 3, and here we go, 3. Okay, now what we're talking about in terms of a rotation, and that rotation is clockwise, means that you actually take the entire point from the center of rotation, which in this case is the origin, and we rotate it clockwise. By how many degrees? By 90 degrees. Okay, the common rotations that come up regularly in the syllabus are 90, -90 being in the anti-clockwise direction, 180 and 270. Okay, you probably, more than likely in grade 11, you're going to get nice numbers that look like that. And because we get those nice numbers, we have very exact ways of dealing with them. Okay, so this is now a 90-degree rotation, and you can see this point has swung across to that point there. We indicate the transformation with that little apostrophe like that. And in general, if the point was x comma y, okay, and this is a rule that you need to learn by heart. I'm not telling you this because I like being here. I do like being here, but I'm telling you this because you need to actually know this by heart. Okay? In other words, xy, after the transformation of 90 degrees, it becomes y minus x. Okay? So if we think about it, this graphical is really easy to use because it's on graph paper and we can actually see the coordinates. Very easy to see -1 and 3. Okay? So before I even think about what's written here, let's see if we can read the coordinates off the graph paper. Okay, obviously, I've got an x value of 1, 2, 3. So my x value here is 3. And I've got a y value of, well, it's 0, and then I'm only going 1 up, so it's 1. Okay, which basically means that my coordinate looks like that, 3, 1. Okay, now what has happened? Okay, what has happened? The rule says that xy, okay, the x went to the y value and became negative. So the minus 1 went to the y value and became negative. And what is negative, negative 1? It's positive 1. So that actually looks right to me. And then xy becomes yx. So the y value that was there now becomes the x value. So if the y value here was 3, it now becomes the x value 3. Okay? And you can apply that rule always. Okay? The reason why that rule works is right here on the diagram. You cannot unprove or disprove this. If you take any point anywhere in the Cartesian plane and you rotate that from the origin, in other words, you draw an arm to the origin like that and you rotate it, this rule will always work. If you find a rule that doesn't work, send it into the studio and we will give you $1 million. We will give you $10 million. Why? Because this is a theorem, it's theory, and it cannot be disproved. Okay, so learn it off by heart. We then have another rule. Okay, let's keep scrolling down the page here, and that is 90-degree anti-clockwise. So I'm doing the same thing, I'm just going in the other direction. Okay, so the image of a point pxy rotated anti-clockwise through 90 degrees around the origin. P minus yx. Again, there's a generic rule. Again, I say to you, learn it by heart. Okay, so if you've got graph paper, it's very easy to actually work out the rule, because you literally take a point, you join it, you make a 90 degree, and you see where that point ends up, and then you read the coordinates off. Okay? In this case, let's do the same exercise we did earlier. Okay, let's write down the coordinates that we can see. Let's use, okay, so if I've got minus 1 and 3 again, so I've got minus 1 and 3, and that's that coordinate. Oh, that's a terrible 3. Let's redo that. Minus 1 and 3. Okay? Then let's read the coordinates off once I've transformed this by 90-degree anti-clockwise, a rotation. Okay? What are the coordinates? It's minus 3 and minus 1. So minus 3 and minus 1. Okay? So, which is great because we can now prove that what we have as a generic rule is true. In other words, x and y became negative y, so the y went to the x and became negative, so 3 went to the x and became negative, and you can see the 3 became a minus 3. And the y, okay, let's go back there. Hang on, we've just lost.
Something very exciting things going on there.
Okay, apologies for that. Right, we're back in action. So just to talk about the rule again, so our y value and now became, so the new y value is the original x value. So if it was minus 1 there, it's now minus 1 here. Okay, so the rule works and you need to know how to use it. Okay, keep scrolling down here. My image is just moved over here. Let's just move it out the way. So I've got a 180-degree rotation. This is now the next one. So what have we done? We've done a 90-degree rotation in the one way. We've done a 90-degree rotation in the other way. And the next important one, which I want to cover with you, is a 180-degree rotation. Now this is quite easy, okay? When I say to you 180 degrees, you guys should be thinking straight line, okay? Because the angles on a straight line are 180 degrees. In other words, it's a really easy graphic to show, because let's just move this up here so that we can see the rule as well, and that is because you literally draw your point P and you draw a straight line, because this angle here like that is now a straight line. Okay, and I'm not going to write on this, but I think we can see it. Okay, the x value was minus 1. Okay, the new x value is 1. The y value is positive 3. The new y value is negative 3. In other words, the transformation rule that we need to learn by heart here is this rule over here. So we write the rotation as xy becomes negative x, negative y. That's a nice easy one. Okay. Now I repeat to you, learn these by heart. If you happen to forget them, it is so easy to very quickly in 1 minute, okay, just to draw a small grid pick a point. You need to draw it on a grid though. Pick a point and do the rotation. Join the line and do the rotation and see. Remember, you're going to have graph paper. So you'll be able to see exactly, once you rotate, what the coordinates of the new point will be. So if you really have a crisis and you can't remember, it's very easy to work it out because you literally just do this. Okay? But it's really great to know these off by heart. Makes life very, very easy. Okay? So I would say that's a definite plus. You're going to gain a lot of value in learning those three. Okay, now let's see. So that's the theory. Now how do we apply this? Okay? So again, I'm just going to move this diagram up a little bit so that we can read and look at the diagram at the same time. So a very basic example, I've got a triangle XYZ. Okay? And that triangle XYZ, it's been copied onto squared paper. The coordinates are given on the picture. Okay? Now you can't really see it here. I'm just going to try and put in the center for you. Okay? And if this is 4, then this is the center here. So if we just think of this here as being, okay, let's see if we can get a better color. Let's use a green. And this here is our axes. And 1, 2, 3, 4. This here is the axes as well. Just so that you can see the origin in this diagram, just for the purposes of explaining this. Okay? Hang on, let's try that one more time. And that is, we'll just extend that here. Okay? So, it's a bit untidy, but I think you get the idea. Okay? So, first of all, I see my coordinates. 4, 4, y minus 1 minus 4, and z minus 4 minus 1. Okay, now what are we asked to do here? So, rotate the triangle XYZ anti-clockwise through an angle of 90 degrees about the origin to give triangle X, Y, and Z transform, so apostrophe. And now we're going 90 degrees about the origin, okay? And it's anti-clockwise, so it's that way. So if I then think about what my diagram will look like, okay? Hang on, so there's a second part to this, but we'll come back to that. I just want to deal with part A. Okay, so before we do it, let's just think about what's going to happen here. Okay? So I want to just erase this green because I think it's a little bit messy and we're just going to talk to it. So if this here is the origin, I'll just indicate that. That is my origin. Okay? Now, if I'm going to rotate each point by 90 degrees, what you can do is you can think about this as being points from the origin. And those points, they go there, and they go there, and of course they come down here as well. Okay? So it's those points over there. But I'm just going to work with a 1 point. Okay? So this point X. X, 4, 4. Now, when I transform it, it needs to go 90 degree anti-clockwise. Okay? So if I create something that looks like this, I'm going that way. Okay? And the new point is going to swing across somewhere there. So I'm kind of expecting, and I have an expectation, that this new point is going to be somewhere in there. Now, we have tools that allow us to work out what a coordinate pair becomes. So let's quickly do this. Okay? So if you remember the rule above, the image of a point pxy rotated anti-clockwise is this rule here. xy becomes negative yx. Okay? So if we then take the 3 coordinates and apply the rule, okay? Let's apply the rule here. Obviously there's arrows that are just missing in here. Okay? But this is what it becomes. Okay? So that's what that becomes. That's what that becomes. And that's what that becomes. Okay? But 4, 4 becomes minus 4, 4. How do I get that? 4, 4. Okay, so the y swaps and becomes negative. So the 4 comes to the front and becomes negative. And the x moves to the end. Let's do the next one. Minus 4, that will become my x value, but it will become negative. So minus 4 becomes 4. And the minus 1 simply moves across to the y position. In other words, the x becomes the y. And lastly, minus 4 minus 1, okay, the minus 1 comes to the x value and it becomes negative, and obviously your minus 4 becomes minus 4. And then really it's just a case of plotting those. So I would say it's better not to do these questions graphically, okay? It's better to understand what's happening graphically, but when you really work out the coordinates, use what you know in terms of the rules, okay? This rule here, just apply it. It's really, really straightforward. Okay, so let's go down here and see what this image looks like. So obviously this is the new image here. It's that one there. And you can see here, if this is the origin, okay, let's just indicate the origin here. So this here is the origin, and that's the origin over there. And your 4, 4, if I now join these, in other words, I join the 2 points from the origin, you will end up with a 90-degree angle between the two. So I'm not going to do it, but if I join that to there and that to there, right, you're going to end up with a 90-degree angle between the two. Okay? So 4, 4, and this point here, Z, okay, what does that become? It becomes 1 minus 4, so that's swung across by 90 degrees like that, anti-clockwise. And lastly, this point here, it's swung across to that point there, and if I join those two again, you'll get an angle of 90 degrees. Okay? So I hope you can see that. It's just to illustrate how this works in theory. And okay, I mean, that's really it. Okay, there's another question here, which I just want to do before we go to an ad break. And that second question, what it spoke to was rotate triangle XYZ through 180 degrees now. So we've just done 90 degrees. Now we're going to do 180 degrees. And again, it's really just a case of applying the rule that I've just shown you. So very quickly, if I then go down here, and I apply that rule. So here is the rule, okay? The rule says that on 180 degrees, xy becomes minus x minus y. So I haven't filled those in so that we can do it together, okay? We'll try this. Let's see if it works. Okay. So 4, 4 obviously becomes minus 4, minus 4. Nice and easy. Minus 4, minus 4. Let's try one more time. You might have to just call them out. Minus 4, minus 4. Okay. Your y being minus 1, minus 4 becomes 1, 4. 1 and 4. Okay. And lastly, minus 4, minus 1 becomes 4 and 1. Okay? Becomes 4 and 1. In other words, I've just kept the x and y where they are, but I've negated the values. We can draw this, okay? I'm not going to draw it. On the diagram, I'll just give you a very rough sketch of what it looks like, and obviously in an exam you may or may not be asked to do this on graph paper, but really if you just have a Cartesian plane, then minus 4 is somewhere down here, okay, where that's your y is 1, 4, so it's somewhere up here, and your z is 4, 1. 4, 1, it's somewhere. So you're going to have something that looks like that, and obviously we need to do it to scale. Okay, struggling a little bit with my diagrams today, but I think you get the idea. Okay, so it's really just a case of joining those dots. Okay, so I think that's quite a nice introduction in terms of rotation. I've still got enlargements to do with you, but I think we're going to kick it back to Indiana, and we'll just see what she's got to share with us.
Fantastic, guys. I think what we're going to do is we're going to take a little break. I just want to quickly say, for Linda, Harry, I know that a few of you say that you lost. Please tell me where you are lost. And Nele, I know that you guys are a bit lost with what we've been talking about, but if you show us where, it'll work much faster, much easier for us. So what we're going to do is we're going to take a quick break. You guys go get a cup of tea, a glass of water, get those questions in, and don't forget, we'll be answering them in the last 15 minutes of the break. See you after the break. Hi guys, and welcome back to Learn Extra Live. Big thanks to Liberty for making this all possible. You guys rock. I hope you're all enjoying the show. Anele, keep those questions coming. Georgina, keep those questions coming. I also just wanted to say, Matlogonolo, I know that you guys, that you're busy today, but she wanted to say thank you because she received her Cassia calculator. So super happy about that. I'm so glad you've got it. I think what we're going to do now is we're going to go straight to Yuval and get straight back on it. Guys, hope you're watching, hope you're learning more, and I hope you're learning extra.
Alright, so we've spoken about rotations. The next thing that I want to cover with you is about enlargements of a polygon. And remember, a polygon is any closed object, so it's ranging from a triangle to squares and rectangles to pentagons to multi-vertexed figures. So it could have 8 sides, 10 sides, 15 sides. Okay? In this particular shape here, if you think about your figure HIJK, okay, that's this one here, HIJK, it's a 4-sided figure, okay? And it's, I mean, we can read the coordinates off, right? So it's got coordinates 3, 3 for I, 2, 2 for H, 2, 1 for K, and 4, 1 for J. Now, in the figure, this quadrilateral, it's been enlarged by a scale factor of 2. Okay? So enlarged by a factor of 2 through the origin to become H prime, I prime, J, K. Complete the following table using the information in the figure. So just before we do that, okay, an enlargement means it's almost like a clone of the original. In other words, you simply take your original figure, you don't change the orientation like we did in a rotation, you don't change the shape like we do in a glide, you simply, or in a reflection, maybe you change the orientation, you flip it the other way. An enlargement is strictly, it's whatever shape it was, simply bigger. All the angles remain the same size and all the sides grow in the same proportion or the same ratio. It's a very important word when we're dealing with scale factors and enlargements. Okay, so two kinds of transformations that I'm doing today, rotations and enlargements. For rotations, you always need to know the angle. For enlargements, you always need to know the scale factor. Okay, so the table looks like this. Okay, it's initially asking us what are the coordinates. Okay, now I don't really have that much space here, so I'm not even going to try and write down the coordinates here because I think it's just going to be a little bit difficult. Rather, what we'll do is we will talk to the coordinates. Okay, so this is a table where I'm meant to complete the original and what is the transformation, and we do this by reading it off the diagram. Okay, so I'm just going to do one of them. I'm going to do H because it's just a little bit small here, so I would like to do H, and I'm going to write it in green. Okay, so what are the coordinates of H, the original H? It's 2, 2. Okay, 2, 2. So H is 2, 2. 2, 2. What is H prime? H prime, let's read it off. H prime is 4, 4. 4, 4. Okay? 4, 4. Let's just talk about one more. Okay, let's talk about I. Maybe we can do I in here. So I'll just do one more. So what are the coordinates of I? Okay, if you think about I's coordinates, it's 3, 3. Okay, and what is I prime? It's 6, 6. Okay, so I hope you can start seeing the pattern here. I is 3, 3. And I prime is 6, 6. 6, 6. Okay? So before we give you the clue, there's a question here, or rather the answer, there's a question that gives you a clue. It says, what conclusions can you draw about the coordinates? Okay? And the coordinates undergo the transformation, and then there's a rule. Okay? And I hope you can see it here. What has happened to each of these numbers? The 2 became a 4, the 2 became a 4. In other words, they've doubled. What would happen if the scale factor was 3? Okay, these numbers would triple. In other words, what would happen if the scale factor was a half? So now it's not an enlargement, but it's a reduction, but the scale factor is a half, so these numbers would halve. Okay, in other words, when you plotted it, you'd end up getting a smaller object than the original. So I hope you can now see that the generic rule is to say if the original coordinates are xy, the new coordinates become xy multiplied by your scale factor. So here is the general rule. It says the coords undergo the transformation xy becomes cx cy, where c is the scale factor. Okay? And then so that's a rule, that's a very important rule, okay, and I've just shown you that, and you should learn it by heart. This rule will always work when your center of enlargement is from the origin. And what that means is that if you draw a line from the origin to any corner in your original shape, that same line should touch the corresponding corner in your new shape. Okay, so if you swing it out like that, both objects will always lie inside those lines. So you can see here, if I draw a line K and K prime are on the same line. Okay, J and J prime are on the same line. And that is because the center of enlargement is my origin. So remember, the same as in rotations, you always need to know what the center of rotation is. Here in enlargements and scale factors, you need to know what the center of enlargement is. And it's normally the origin. Okay? What else is being asked in this question? So that's the first part. So we've got our generic rule. It then says the lengths, when we enlarge by a scale factor of 2, okay? And of course, the lengths, so the hint here is that the lengths in this case will double, okay? So I don't want to get too much into exactly what the lengths are, but if you say, for example, that the length of line HI is maybe 1 unit or root 2 units or whatever the case may be, it's going to double when you go from H prime to I prime. Okay, so that length there, and you can see it from the corner to the corner, so it's just going across one cell, and over here it's going across 2 cells, so it's exactly double the length. And any one of these lines, if you take the corresponding line in the transformed object, you'll see that the length is exactly double the original length, and that is because the scale factor was 2. So 2 very important things that come up in scale factors is actually also area, and if we get a chance we'll talk about that later. But what I've spoken about is that to get your coordinates of your transformed object, you simply multiply x and y by the scale factor. And the other thing that I've said is that all the lengths in the object, right, they will also be multiplied by the scale factor in the new shape. So if your scale factors are half, each corresponding length will be exactly half the length of the original shape. Okay, I hope that makes a lot of sense. There is another example here which I think is quite useful. Okay, and I think we'll just head back to Indiana while we find it, unless it's down here. Let's have a quick look. So what we'll do is we'll head back to Indiana. We'll just see what you guys have been responding to us with, and I'm going to see if I can locate the next enlargement question.
Fantastic. Okay, what I think we're actually going to do, guys, is that we are going to take a break. However, Yuval has said that he is going to go over, let me just have a look here. We're going to do a summary of both rotations and enlargements. So that'll be pretty cool. Guys, don't forget to get your questions in on the page. We are taking questions in the last 10 minutes. There are so many grade 11s on the page. I think it's so awesome. Sylvester, welcome. Mapapuli, welcome. Guys, keep those questions coming. And you know what? We'll see you right now after the break. Hi guys, and welcome back. Okay, I know Sylvester, you asked for a challenge, and Yuval is going to give you that challenge. Guys, we're also going to be doing a little summary. Stay stuck to your seats, don't go anywhere. This is where everything starts to get exciting. Yuval, take it away.
Okay, so here's a nice question that I'll hopefully get to later, but in the meantime, it's a nice challenge for you guys just to try it. Obviously, I'm going to do a little bit of a summary after we do this question. But I just want to talk a little bit about this question, and then I want you guys at home to think about how to answer this question, okay? So what we have is we have triangle STU, and we have an enlargement. You can see that because obviously it's bigger, and it's S prime, T prime, U prime, okay? You can see the coordinates. I'm giving you some hints here, and the questions for this thing are write down the coordinates of the original and the coordinates of the transformation, and then I want you to give me the scale factor, okay? And there's one more question which I'm going to throw in there just for good measure. So I want the coordinates and I want the scale factor, and the next question that I want to ask is by how much bigger is the area of the enlarged object, okay? So by how much bigger is the area of the enlarged object? Hopefully we'll get an opportunity to talk about that later on, okay? So I'll just give you another sort of 10 seconds just to take that in, and I'm sure that we can make a plan to post it, but that is STU and the enlargement of STU. Okay, I'll just give you 5 seconds just to write that down, and then we're going to go into a short summary. Okay, so I mean, we've spoken about I'm just going to use my little cheat sheet here so I remember to give you everything. We spoke about 90-degree clockwise rotation. So let's find the pen. 90-degree clockwise rotation. Clockwise. Clockwise rotation. Rotation. Okay, and we said that that is when xy, what does it become after the transformation? It becomes y minus x, y minus x. So we'll do an example as well. So if I have 3 minus 5, right, what does it become? Okay, so the y moves to the front, so minus 5 moves to the front, so it becomes minus 5, and the x becomes negative x. Right, so 3 becomes minus 3. Nice and straightforward. The next one, okay, I'm just going to make these bullets so that you can see. The next one in the list is if I do 90 degrees anti-clockwise. Okay, 90 degrees anti-clockwise, so that's my next bullet point here. So I've got 90 degrees anti-clockwise, anti-clockwise, and what is the rotation? Okay, obviously your x and y, what is it going to become? And it becomes minus y comma x. Right? Minus y comma x. So over here it was y minus x. Now it becomes minus y comma x. And if I do an example again, okay, I'm going to use 2 and negative. I'm going to use minus 2 and 1 maybe. Minus 2 and 1. Okay, what does it become after the... So the x moves to the end. So the minus 2 moves to the end, minus 2. And what happens? Okay, your y moves to the front and becomes negative. So 1 becomes negative 1. Okay, and the last one that we covered in terms of rotations was that story with 180 degrees. So I've got one more bullet here, and this is now 180 degree rotation, and the rule is x and y becomes negative x, negative y, and if I have minus 5, minus 7, and remember, if you've got an entire object and you can see all the coordinates, you just apply this one by one. So you apply this little rule to every coordinate in order, and then you draw the picture once you've got all your coordinates. Okay? So this becomes now 5,7. Okay, so the next thing is when it comes to enlargements. Okay? So let's rule a line there, that is rotations. When we start talking about enlargements, okay, there's really 3 things which come up. Enlargements, and that is, first of all, okay, your coordinates. Okay, let's use the same notation as before, so we'll put a bullet here. So the rule for coordinates, the rule for coords, standing for coordinates, is you have x and y, and what does it become? It becomes cx and cy. In other words, if c is the scale factor, if c is 3, so the scale factor of 3, then if you have, I don't know, let's make it up, if you have 5, 7, what does it become? It becomes 5 times 3, which is 15, and 7 times 3, which is 21. And those will be your new coordinates. Okay? So that's the rule for coordinates. In terms of lengths, your lengths will be multiplied, your new lengths, okay? So your new lengths, I'm just going to write here lengths, okay? Your transformed length, I'm just going to use this notation here, transformed length is equal to c times your original. In other words, if the original length was 5 units, it's going to become 5 times 3, which is 15 units. Okay? And the last thing I want to speak about is in terms of areas, and the easiest thing to do here is to talk about squares when I talk about areas. So if I've got a 1 by 1 square, the area is 1 because length times breadth is 1. Okay, 1 times 1. If I then use a scale factor of 2, and in other words, I enlarge the square by 2. So what's happened is the lengths have become 2 and 2, so it was 1, it's now 2, but the area is not being multiplied by 2. The area, length times breadth, is now 4. Okay? And if I make this thing 3 by 3, the scale factor here is 3 because I've just made it 3 bigger than the original, but the area becomes 9. Okay? So there's a hint there. Your area, to get your new area, you've got to use your scale factor squared. Scale factor, because you're working with units of area, you've got to use your scale factor squared. So if I've gone with a scale factor of 3 here, if the original area here was 1, 3 squared is 9. Okay? So if I take any object, just to extend on this once more, if I take any object, let's say I take this object here, and I tell you that this area is 7, okay, and then I take the same object and I enlarge it, okay, I enlarge it by 2, so the scale factor is equal to 2. Now I'm not telling you what these coordinates are because it's not important. The area here will become 2 squared times 7. In other words, it will become 4 times 7, which is 28. Okay, units. So I hope that makes sense. The scale factor, right, was 2, so it becomes 2 squared bigger than that. And 2 squared bigger is 2 squared times what it was before. Okay, so that's just a nice summary. I think if we have some more time and we don't have questions, we'll still go back to that previous question. But obviously this is, there's a lot going on here, so keep those questions coming. We're going to hand over back to Indiana.
Okay guys, I have pasted the picture from Yuval's challenge on the Facebook page. So what you can do is you can get your phones out, download the picture, have a look at that and get those answers in. I think what we're going to do is we're going to take a quick break. Guys, we're nearing up to the 10-minute mark where we're going to be answering all of your questions. So if there is anything that you aren't understanding, please get them in now or forever hold your peace. Don't forget, the only silly question is not asking the question at all. Okay, we'll see you now after the break. Hi guys and welcome back. We are now going into the last 10-15 minutes of the show. I can't believe it. It shows you that time flies when you're having fun. I just wanted to say, guys, also help each other out on the page. Matlogonolo has said if anyone needs help, she will help them. So thanks for being a mindsetter lady. Natalie said she hasn't even started this section yet in school, but she's understanding it already. So that's awesome, guys. So guys, get those questions in, and Yuval, I think take it away for those last 10 minutes.
Alright, so this is the question that we challenged you with, okay? And I hope that most of you were able to work out what's happening here. Remember, we had this triangle STU, we had an enlargement S prime, T prime, U prime, and okay, you can read the coordinates off, and we were then asked to write down the coordinates of the original, okay, and also to identify the scale factor. So the first part should be really straightforward. Okay, obviously, if those of you didn't manage to draw the picture accurately, that would be a problem. But I mean, we can talk through the coordinates quite quickly because we can just read them off. So U41, S32, and T54. After the enlargement, okay, S has become 6, 4. U has become 8, 2, and okay, I think maybe what we must do is write that down. So let's write it down one by one. So S has become 6, 4. Let's quickly write that down.
If you want, I'll write them down
so
for you.
So S has become 6, 4, 6, 4. Okay, what has U become? U has become 8, 2, 8, 2, 8, 2, And lastly, what does t become? T is 5, 4, and it's become 10 and 8. Okay, 10 and 8. So the reason why it's quite nice to look at this all together is because you should now be able to see, okay, what is the scale factor? Remember, the rule for scale factors is to say, I multiply both the x and the y to get my new transformed coordinate. So what number is the common multiplication factor, or the scale factor, that I've multiplied each of these coordinates by in order to get my result here? S prime, U prime, T prime. And it's quite obvious. You should all be able to look at it and see it immediately. It's a scale factor of 2y, because 3 times 2 is 6, 2 times 2 is 4. 4 times 2 is 8. Okay, 1 times 2 is 2. 5 times 2 is 10. And 4 times 2 is 8. So the scale factor is, of course, 2 units. Scale factor is 2 units. And I asked you another bonus question. Okay? And the bonus question was, by how much bigger is the area of the new shape in comparison to the old shape? And it's 2 squared bigger. And because the scale factor is 2, 2 squared is 4, the area, if I had to buy paint to paint this triangle here, let's just undo that, I would need 4 times more paint than the original STU. And how do I get that? It's S prime, T prime, U prime, okay, the coordinates, and the scale factor is 2, 2 squared is 4. So it's 4 times more. A very common exam question for the matrics, okay? Okay, it's come up in tons of past papers, really, even kind of final papers, is they talk about area and the area of the old shape over the area of the new shape. Okay, and really it's just a case of working out the scale factor squared. So if the shape is smaller, then it's a half squared bigger. A half squared becomes a quarter, so it's a quarter less than the original. Okay, so it's quite a straightforward question. I've got about 5 minutes left, and some of you have been phoning in and asking and tweeting in and Facebooking in and asking about some coordinate geometry kind of questions. I've been speaking today mainly about transformations, okay? And the reason why I'm doing that is because we're still doing another show next week and the week after in the grade 11 slot, where we will be covering those grade 11 coordinate geometry, straight lines, all those wonderful things that we do in analytical geometry, coordinate geometry. But just because I want you guys to feel like you've gotten what you asked for, I can't remember exactly who it was, but somebody asked about an angle of inclination question, and it's worth just doing a kind of 1 or 2 minute example just to show you how you can get that angle, okay? So the kind of questions that come up normally when we ask about an angle of inclination, it's an angle, if this is the Cartesian plane, then it's the angle that your line makes with the x-axis, and it's theta degrees, okay? And we basically use this rule that m is equal to tan theta. And that is the theory that you need to know for this section, m being the gradient of the line. So just as an example, if I tell you that this is y equals 2x plus y equals 2x, because it's got a y-intercept of 0, so I'm just going to make it 2x. To work out the angle of inclination, I'm going to say 2 equals tan theta. Okay? And I don't have a calculator with me, but I'm sure all of you can use shift tan of 2, and that will then give you your theta degrees, and that is the angle of inclination. Okay? Don't get confused if you see a similar question with a line that has a negative slope. So for example, if I draw a negative line here, okay, the angle of inclination is always read from the positive side of the x-axis. It's not this here. It's not that there. It's not that. Okay? It is this angle here, the one from the positive x-axis going like that. That is the angle of inclination. Don't get that wrong, okay? It's a potential trap. So if I then just make this up and we go, the straight line is y equals minus 3x plus 2. Again, I'm going to say minus 3 equals tan theta. And then I've got to use what I know about general solutions and trigonometry and trig equations to work out my value of theta. And I can see that theta is an obtuse angle. So your final answer, you'll go theta is equal to, and you're going to go shift tan, and you're going to go 180 minus, and that's going to give you your answer. Okay? So that's angles of inclination, comes up matrix as well. I mean, it's a perfectly fair exam question. I've seen it lots of times before. The extension to this is very often you may get, and I'm just going to show it to you without actually doing it, is about having two lines and then being asked to find the angle between the two lines. Okay? But I think we're going to save that for another day. So, do we have a question?
We do. We've got quite a great question. Ebenezer, thank you for sending through such a fab question. Okay, Yuval, he wants to know, does the area increase by the same factor for all shapes?
Okay, so I'm not exactly sure what you're asking there, Ebenezer, but it really, you know, the shape, it depends on what the scale factor is. Okay, so if I'm understanding your question correctly, the answer would be no, because it depends on my scale factor. So if my scale factor is 5, the area will increase by 5 squared. So it will be 25 times greater. If the scale factor is 7, the area will increase by 7 squared, which is 49. The area will be 49 times greater. If the scale factor rather is a half, for example, in other words, your shape is becoming smaller, okay, your new area will be a half squared smaller. So half squared becomes a quarter, it'll be a quarter of the original area. So I hope that really answers the question.
Okay, I hope so too. I think Malilo, I think you've just kind of answered her question as well. She said, what happens when the number is bigger than 7 or 6?
Nothing happens.
Bigger and bigger.
Yeah, so Malilo, don't be afraid of big numbers, okay? It works. The theory is working for any number under the sun. You can take a shape and you can increase it by 100 if you want. No one's going to ask you to draw that on graph paper because it'll take you the next couple of weeks. But the theory works. If I take a shape and I use a scale factor of 100 and I say to you, what is the area of the new shape? It is 100 squared times bigger, which is 10,000 times bigger. So the scale factor is just a number. Normally, because we're working in an exam and because we're working with manageable numbers, okay, you'll get nice scale factors like a half or 2 or 3, maybe 4 or 5. But the theory works for all numbers.
Fantastic. Okay, guys, grade 11s, thank you so much for tuning in to Learn Extra Live. We've had a fantastic session. Grade 12s, don't forget that you're next. I know that you've been watching since grade 10. Obviously, grade 11s, thank you so much for learning more and learning extra. We'll see you same time, same place next week. See you then. Bye.
Bye.
Are you on for another one with me?
No.